Now that we know what rectifiable curves are in a space and that they admit arc length parameterizations, or more generally Lipschitz parameterizations, we are ready to define what we mean by a real valued function being absolutely continuous on a curve. So you are on a space X. It's just a metric space. It can be really wild, but of course I cannot draw really generic pictures. Here's some curve. And what do we mean by U restriction to this gamma being absolutely continuous? And the answer is that we call this absolutely continuous if its composition with the arc length parameterization of gamma is absolutely continuous. Remember that if we don't arc length parameterize a curve, even if a curve looks as nice as a straight line in R2, you can have the worst parameterization of this. You can have the counter-Vitali function, which goes from this end to this end, and you can take constant u to be, the function u to be just constant 1, and already we see that this is not absolutely continuous, and you do not want to call the constant function not absolutely continuous. That is why there is this necessity to first correct the possible horrible parameterization of the curve, and only then look at the behavior of the function along the curve. You want to make this parameterization canonical. That's why this arc length parameterization is so important. So we call a function, again, u, absolutely continuous on a curve if after reparameterizing by arc length, u composed with alpha, which is basically gamma, becomes absolutely continuous. Example is when you have let u from Rn into R be C1 and gamma from AB into Rn also C1, which makes it also Lipschitz, and therefore it is a good enough parameterization. Now you can see that u composed with gamma from AB again into R is C1. Indeed, this u composed with gamma derivative at t, it's a nice exercise in multivariable calculus, is gradient of u, which is a vector evaluated at gamma t. So far this is a vector. Gamma prime of t is another vector, and if you dot product them, you get a number, and that's the derivative of this function. It also follows, incidentally, that u o gamma at 1 minus u o gamma at 0. I had b and a, sorry for that. We know because this is a C1 function, the fundamental theorem of calculus holds. So this will be from a to b of this quantity. So gradient gamma t dot product gamma prime of t dt. And this is not just for any a and b. You can turn it into any two other input. And what I'm going to do is u o gamma, let me write it this way, gamma of t2 minus u of gamma of t1 will be this. And look, if I put absolute value here and then I have absolute value on the integral. If I put absolute value in the integrand, I only get a larger quantity, so from t1 to t2. But then we have this identity that a dot b is less than length of a times length of b. So this will be gradient u evaluated at gamma t times length of gamma prime t. It's a vector, you take norm. And I want to get somewhere which will be relevant for metric space picture. And that's why let me add this assumption. If gamma is arc length parameterized, then remember that it's an isometry. So if you write definition of the derivative, this difference quotient, and you take absolute value and limit, you will see that this quantity will be equal to 1 in fact. So we end up with this, that the value of u at different points along the curve is less than or equal to, from t1 to t2, of this gradient u absolute value evaluated at gamma of t dt. And somehow I like this better than even this equality here. Okay, here you have a precise equality from fundamental theorem of calculus, but you have an inequality here. And guess what? The reason I like it better is that when you look at this, there is the u, and then there is gradient of u. There is no notion of gamma prime here, and this is an object on your, object on your metric space X, which is Rn, and this is u is an object, a function. U is a function on Rn, which is your X, and then this is another object on X, and this is showing that along this curve, if I look at 2 points here, gamma t1 and gamma t2, the amount that u has changed is governed by integrating some quantity that is also a function. Gradient u is a function again on x, from x to r, one real valued function. And this is the picture that we want for the metric setting. We don't want this quantity, because this is not an object on your metric space. This is an object in R1. This is derivative of the real valued function u composed with gamma. Okay, and then in the discussion of absolute continuity of functions, we had a characterization. This was in video 3, that gamma is, or not gamma, so a function on R, so R to R function, is absolutely continuous if and only if there is G in L1 of AB such that f values, so f of x values, are obtained from integrating this gt dt, plus this, of course, necessary fixing scalar factor of f of a. Okay? And the reason why this defines an absolutely continuous function is because integration is an absolutely continuous operator in the precise sense that I mentioned in lecture 3. Now I want to go back to here and to detect then a function is absolutely continuous. In this case, to detect that u composed with gamma t is absolutely continuous, all you need is to have a different function, a new object, with this property. So let me write the details of that out. Let's make a lemma. Suppose there exists some function rho bigger than or equal to 0 on this interval AB, such that for every t1 and for every t2, the quantity u at gamma of t2 minus u at gamma of t1 absolute value. So we want to give away some of the exact precise fundamental theorem of calculus stuff, but all we want is an inequality that this becomes less than from t1 to t2 of this rho of t dt. I must say that a rho that is in L1 of AB. So sorry for that. So rho is non-negative and belongs to L1 of AB. Non-negativity, of course, because I want to always bound a non-negative number. I mean, I didn't have to put it in the assumptions. It ends up having to be non-negative. So suppose that there exists some magical function so that this integral governs that. Then u composed with gamma is absolutely continuous. Absolutely continuous as a function from R to R. Continuous. In other words, this implies by definition that u is absolutely continuous on gamma. So this gives us a sufficient condition on when a function, which is defined on a metric space, is continuous on a curve, on a rectifiable curve, on our, again, living in our space. And in this case, I'm not assuming that gamma is arc length parameterized or anything. So not necessarily. Well, I think I do actually. Effectively, I do. But the important part is that the proof is exactly similar to how in lecture 3 we showed that a function defined by this formula is actually absolutely continuous, because from this inequality we will see that if you have any collection of disjoint tj and tj plus 1 satisfy this, that the summation of the values of gamma, u composed with gamma, between these j plus 1 and j, if you add these over j, there are finite many of them, this will be less than summation over j of these integrals. So tj to tj plus 1 rho t dt. But these being disjoint, this is equal to integrating rho t dt along union of these intervals tj plus 1, union over j. And so, okay, by absolute continuity of integrals, So now we have three notions of absolute continuity. I'm glad I did introduce the absolute continuity for curves itself. So by absolute continuity of integration, for every epsilon positive, there exists a delta positive, so that measure of A less than delta implies integral of rho t dt over A is less than epsilon. This would be even with not necessarily non-negative functions. This is a property of integration valid in much more generality. Refer to lecture 3 for more details. So if this summation of tj plus 1 minus tj, if these length of these intervals add up to less than delta, we get that this quantity here, star, will be less than epsilon. And that's the end of the proof, because that's what absolute continuity of a function means, that for every epsilon there's a delta, and any collection of pairwise disjoint intervals that add up to length less than delta force the function also not to change by more than epsilon. So these are easy calculations, but the main point again lies here. So the goal, or the prediction, will be that for U defined from a metric space into R, we will seek non-negative rho such that when you integrate U, when you look at change of gamma along a path, a curve, the change in U values will be governed by integral from T1 to T2 of this rho is ds. And if you find such an S, if such rho belongs to L1 of AB, the range of gamma, then U will be absolutely continuous on the curve gamma. And this rho, this magical rho, will come from the notion of upper gradients, or not come from, will lead to the notion of upper gradients. With the Rn example, so in x equal Rn example, with U belonging to C1, we saw that this gradient of U evaluated at gamma t is the right rho, following from multivariable calculus and fundamental theorem of calculus. So what this rho would look like on a metric space, and which definition or which assumption to put first, we will discuss in follow-up videos. Thanks for watching and have a great day.